Welcome to lecture 40 of MCS 471 on numerical analysis, and for today in particular about partial differential equations, which we call elliptic. Or more specifically, we will see the Laplace equation, or more better explained, we will study a numerical method to solve the Laplace equation. So the Laplace equation is also called, and better called, the steady state equation. So the previous two partial differential equations we considered, so the heat equation and the wave equation, they depended on time. Here time is no longer an issue. We consider a steady state. And we will apply again the finite difference method, which will lead to a linear system. So this lecture is special in the sense that it is the last lecture of this chapter on partial differential equations. It's also the last lecture of the course. In the remaining 3 lectures, we will review the course materials in preparations for the final exam. So to that end, I will finish this lecture with some concluding remarks about what this course was really about and what is the importance still of numerical analysis. Let's dive into the material. So again, what is a partial differential equation? We consider equations of this particular form where the second order partial derivatives appear with coefficients a, b, and c. We are looking for an unknown function u that depends on 2 variables, x and y. The capital F function includes the 2 independent variables, x and y, as well as the unknown function u and the first partial derivatives with respect to x and y. So the previous 2 equations we considered, the heat and the wave equation, included time as the second variable. Here, y will properly be an independent variable, so time will not play a role. The equation we consider is of the 3rd type, so we classify the partial differential equations in this course with the discriminant b squared minus 4 times ac. When that discriminant is negative, then we call the partial differential equation elliptic. And as a very specific example, we consider the steady state. Here is the general format of the partial differential equation. We also have a very specific notation, the delta, to denote the sum of the 2 partial derivatives with respect to x and y, twice. Something, the twice that we perhaps swept under the rug in the previous 2 lectures is that the functions we're looking at are actually nice differentiable continuous functions. So about the existence of the solutions, there might be other solutions, but we make assumptions on our equations. So we have the Poisson equation and the Laplace equation. In the Laplace equation, and that's the type that we will consider, there is a 0 right-hand side. So the equation is defined over a rectangle. So that's another limitation here. If one might also consider circular domains if one goes to polar coordinates. but this is not within the scope of the course. So we consider a rectangular domain. So for x living in the interval a, b, and y living in the interval c, d. And you see so we have one single equation, and then we have conditions. So this is a second order equation. And here it is a very pure boundary value problem. So we have an upper bound and a lower bound. So the lower bound is given by y equals c. The upper bound is given by y equals d. So the g1 and g2 could be called lower bound and the upper bound function that determines what happens at the upper and the lower bound of our domain. We have a function g3 and g4. G3, which I'm underlining now, is the left bound. So when x equals a, g4 is the right bound. And as this is for a fixed value of x, we have a function that depends only on y. So this is a pure Dirichlet problem. We have given values on the boundary, but we could alternatively also have a pure Neumann problem, where instead of giving the values for u at boundary, we could give the values for the derivatives. And one can also mix. So there's a lot of variation here, but we will stick with this standard format. It's an elliptic equation, so let's verify the discriminant. So the b square minus 4 times a. So we have no mixed term, so the b equals 0, and the a and the c are very simple. So this is a very simple equation, and I see that here there is still a typo. So let me fix this. So here we have a y, not a t. So our Laplace equation, so the equation of steady state, what is the focus of this lecture, is an example of an equation where the discriminant is negative. And in our classification, we call this an elliptic equation. Let's look at an example, a running example. So here is the Laplace equation on a square. So the a and the b are 0 and 1. The c and the d are also 0 and 1. And you could consider this as a backwards problem. So it has a very explicit solution. So x squared minus y squared. And you can see when you take the partial derivatives twice with respect to x, you end up with 1. Taking the derivative twice with respect to y, and we have indeed again a negative 1, so not again. So we have 1 for the first partial derivatives with respect to x, and negative 1 for the partial derivatives with respect to y. So we have 1 minus 1. So this equation satisfies the first equation. And then we can compute, plug in y equals 0, we have x squared. When y equals 1, we have x squared minus 1. So I'm talking now about these two conditions at the lower bound and the upper bound of the rectangle of the square. And then we have the left bound. So we substitute x equals 0, we find minus y squared. When x equals 1, we have 1 minus y squared. So mathematically, this is very nice. So in our numerical methods, we will have an explicit solution. So this is a nice test problem. What could we do with this? So this is not an applied math course, but this could model the temperature distribution on a square floor. Here is how it looks like. So suppose that we have a square room, and on one end of the room we have heating. So let me first locate things. So the coordinate system, so the orientation here is such that the origin is closest to us. So the x goes from 0 to 1, and the y goes also from 0 to 1. So you can see that we are at the cold front. So at the x equals 0, we have 0 and negative temperatures. So you can imagine a room where on one side we have a window that might be open or not, and given the time of year, cold comes in from there. And then at the other end of the room, we do have a heating source. So what this could model would be, so here in particular now, you could imagine a fire or a furnace that is at x equals 1, y equals 0, and then we have a sink at x equals -1 and y equals 1. So the coldest spot is where we are using heat. The highest spot is where heat comes in. So this could be a steady state solution, so independent of time, where this is an equilibrium for the temperature distribution on the floor. So this is not a fully complete model for a temperature distribution, but it kind of is a plausible model. All right, so the picture also introduces already a grid. So we see in the picture that we have a gridding in the x, we have a gridding in the y. So this is the outcome of a numerical program that has computed the solutions to the discretized problem. So we will, we will apply the finite difference method, replacing the second order derivatives by the central difference formulas on a rectangular mesh of points. Here it is. So we have our rectangle with the bounds a and b on x, and c and d on y. So you could see d as the upper bound, c is the lower bound, and we have a left bound a and a right bound b. So we can give names to the four constants that define our rectangular domain. So then we have two important parameters. We do have the number of points, the number of interior points in the x direction, and then the number of points in the vertical direction. So that will determine the dimension of our linear system. So in the picture here, we have the black dots where we know the values at the boundary by the given functions g1, g2, g3, g4. And the red dots are the dots where we want to compute the value of the solution. So we know how to do this already. So let us apply the central difference formulas. So the central differences now introduce two new characters. So we have the step size h and in the x direction, and the step size k in the y direction. So these two depend inverse, the h is proportional inversely to the big M. The little k is proportionally inverse. So if the k gets smaller, the n gets larger. So you see the explicit formulas here. So these are the two new characters that are introduced, but they are depending on the big M and the big N. So the M times N is the big dimension of our linear system. So the M times N will determine the amount of work we will have to do. If we think about work, we think of the big M and the big N. If we think about accuracy, we think of the little h and the little k. So the other important thing that I have to emphasize here are the h square and the k square. So the accuracy of our discretization depends on how small h and k can be. So how much computation can we afford? What can we expect? This is also relative to the precision of our computation. So we compute with 64-bit floating point numbers, but our accuracy will be much, much less. So the accuracy of the solution depends on how much work we are willing to do. So here the difference will be that in the previous discretizations, we had only one dimension of the linear system, so that was typically the big M. Here we have the product of M with N. So computationally, solving these steady state problems may involve a lot more work. So we have the central difference formulas again, and then we compute approximations. So introducing a new letter. So I have the Z, I, J. So we are computing heights, if you remember the picture, and these Z, I, J's, they are approximating the solution at xi and yj. So this is the important definition here for our heights in the two-dimensional picture, or when we apply the discretization. So very similar to what we did last time. But we are computing something entirely different. Also, the amount of work that we will need to do will be totally different. So these are no longer time-stepping methods. So we are solving now an entire linear system in the unknown letters Z, I, J. So how do we get to this? Something that is important here, and let me indicate again in red. So we have the continuous U, and then we have the discrete Z. So where we have x minus a, h, we have I minus 1. Where we have here y plus k, we have j plus 1. So the k square and the h square appear in the denominator. So the points xi and yj are defined. So you can see here that the number of internal points, so we have m internal points in the x direction and n internal points in the vertical direction, the total number of points is m times n. So again, this is a two-dimensional problem. So last time when we worked with m equals 20, that gave us a 20-dimensional linear system. Here, if we work with big M20, big N20, this will give us a 400-dimensional system. So it's important to keep this in mind. The formulas all look the same, but what we actually are doing is entirely different. And again, on the final exam, you will be given a partial differential equation, but it will be up to you to see what type it is. And the type of equation determines the type of action. So the first important thing that you should remember from this lecture is actually the type of equation. Here is what we are doing. So we have our unknown zij's, and we have m times n, many of them. So they are the solution of a linear system defined over a grid of as many points. So the linearity is again apparent. So we have mn data points, we have m times n unknowns. So everything lines up quite nicely. Or does it? So this is so you might think of the formulas that we have again a tri-diagonal linear system, but that is not the case. And if you think about this now a little bit, so in a way the lectures are always kind of awkward. Before you realize what the problem is, the solution is there already. So what is the problem here? As I try to indicate already, we have the m times n. So we have a two-dimensional problem. So our unknowns are actually also a two-dimensional grid. So when we think about solving a linear system, we think about ax equals b. So let me mark that down here. What is the problem? So thinking that we have everything worked out already, well, we have ax equals b. So in the second part of the course, we always try to reduce our problems to something that we know already. So what we know already is to solve a linear system of ax equals b. What is the problem is how to reduce this single equation here, but there is a double index. So here notice the I and the j, they are running over m and n. So we have to reduce this format, figure it out so that it fits within the context of a linear system solver. How are we going to do this? We are sorting things, and we're going to sorting things in the dictionary way. So think about sorting names. We are going to sort pairs of indices in the lexicographical order. That's the standard order. So we have 12 points. So normally this is a grid that is way too coarse for practical purposes. But here you see the 12 points, and we label them uniquely. So every point has already a unique name, but it's a first name and a last name. So first index and a second index. We want a unique number. And how can we map this? Well, we sort the points in lexicographical way. Think about the points now as letters instead of numbers. So we would have A, B, C, D, although this is now bad because we have already used the A, B, C, D. But consider the numbers so as we would treat them as they were letters. So the first letter is 1. So here we first take in our order as we order this here, 1, 1 is smallest, so comes first, then 1, 2. So the first 3 points, here are the first 3 points, all with the same first smallest number. And if two numbers have, if a tuple has the same first index, then we look at the second index to sort. That's the same as you do in a dictionary. If you have two words that start with A, then you look at the second letter to sort them. That's how we do. What has the advantage to this? So notice that there is a formula for this. So you may have done this when you were ever programming with matrices. Matrices are actually also stored as one-dimensional arrays. So some higher order languages, many higher order languages, allow you to pretend like you can work with two-dimensional data structures, but there is a mapping. You either map row-wise or column-wise. So here you see that we have the mapping that is more column-wise. So the second index is the lead index. So all elements in the first column are actually coming first. So we have this general formula here that describes the mapping. And we will use this formula then in our program. So it's important that we remember this. All right. Now it gets technical. So the goal of the order is that we get to a Julia function that will allow us to do some computation. So we will not, and sometimes we do in this course, but actually computations are better left off to computers, and for that we need functions. So we will apply the relabeling. So here in the relabeling, it might seem subtle if you look at these formulas, but we have the little z, and then we have the capital Z. So here you see the one-to-one correspondence. So for every pair I, j, we have a unique index. And the big Z will be our long vector, which is the x in the system AX equals B. So you see the B is already coming in here. The right-hand side comes in. Very similar to the problems that we had with the wave equation, we have indices that are zero or that are outside the bound. Now, in this lecture, since this is the last lecture, let's not overcomplicate things. We are working with pure Dirichlet problems, so we will not need to do any central differences. So we will just use the given boundary values defined by the four functions. So there is progress. So there are two main formulas on this slide. So the top formula is the general formula in our letters, original letters, as we see the two-dimensional grid. The second big formula here is the formula that is suitable for the linear algebra. So this formula defines the coefficients in the linear system. Whenever we talk about the linear system, we see a matrix. So let's try to define this matrix. So A matrix is again two-dimensional, so we have to define what are the coefficients on each row and on each column. So we have the row index and we have the column index. So the equation that we derived in the big Z defines the coefficients of the two-dimensional matrix that we will use to solve the linear system. So one can think that we are having a tridiagonal system, but that will not be the case. So this is still not apparent here, but one can look at the rows and the indices. We will see that we will not have a tridiagonal matrix. All right, so we have the general formula. Then we have to use the boundary values for the special cases. So we have the four functions which are now given names: bottom, top, left, and right. So the bottom and top correspond to when we are at the case when I equals 1, j equals 1, I equals m plus 1, j equals n plus 1. So in those cases, we have a right-hand side, and in those cases, when j equals 1, then we have another I index that runs, and you can also see these formulas. It's all very straightforward and starts to get very repetitive and a little bit boring if you see the right-hand side formulas. Depending on which index you keep fixed, you know which function to use. So the first two functions, the bottom and the top, depend only on x. And this is the function that you will use when you fix j. If j is fixed to the lowest index, then that means that for j equals -1, you are at the left. So in a way, these formulas, when j equals 1, you are at the bottom. I was about to say that it's unfortunate that they are not sorted, but they are sorted. So there is a correspondence where we have bottom, top, left, and right, and here we have the 1, 2, 3, 4. So you can see the regularities G1, G2, G3, and G4. So this is a puzzle, but it all fits. All the pieces are fitting, and it is a very highly structural formula. So notice also the step sizes, so the k square and the h square that are coming in here. So this defines the right-hand side. So we now have completely defined the linear system. Here are some questions. Some question that is actually answered when we look at the posted Julia code. So the purpose of this exercise here within the lecture is to phrase some questions that we have now. We have a general equation, and it would make sense perhaps to derive a stencil, but actually the stencil here is the entire grid. So the matrix is not tridiagonal. So we have used one particular lexicographical order. One could also use a reverse lexicographical order, or one can also look at the sums of the indices. That is the degree lexicographical order. So the question is, could it be that for some orders, you get a linear system that has a more favorable structure? It's kind of a surprise that we end up with a dense linear system. Is it not possible that we could have a tri-diagonal system. So one can think about why this would be possible or would not be possible. Let's now go to the Julia code. So there is one example that we have, the running example from the beginning, and that was the data was so the plot was made with the numbers that are computed by this function here. So the Laplace, so it solves the Laplace equation. So the right-hand side is 0. So a more general setup would be a Poisson function, where we would also have an additional right-hand side function. Here we have the 4 functions that respectively define the bottom, the top, the left, and the right. So the example shows possible functions. So the example contains valid code, and it will be giving us a system of 12 unknowns. So there is the big M, which is 4, and the big N, which is 3. So we have 12 unknowns. So we will return a matrix of, in this case here, 12 unknowns. So the M and the N are the leading dimensions, so they determine the amount of work we are doing. For the decomposition of the interval A, B, so that is the M, and then perhaps another color, we have the decomposition in Y with the N interior points. So these are the 2 leading dimensions when we think of the amount of work we will have to do. When we think of the accuracy, we think about the H and the K. So they are defined here. As always, there is some thought that needs to go in. Is it now +1 or -1, or do we just divide by M or N? So think about this a little bit. So if you have to decide this, think about the M equals 4, the N equals 3. Solve it for one particular case, whether it's +1 or -1. So what is determined here is the dimension. So we have the initialization, the data allocation, if you like, for the linear system. So the leading dimension is M times N. So we allocate space for the coefficient matrix and for the right-hand side. This function defines the right-hand side first before the coefficient matrix. So for the right-hand side, we have the evaluation of the boundary condition functions. So we translate here the formulas that were derived earlier. So the right-hand side will accumulate. So we have the cases where we are running on the bottom or running on the top, running left or running right. Dividing by k square or h square with the indices. So here is where we do the puzzling. We have the formulas for the definition of the matrix. So the correctness of this function here depends on the formulas, correctness of the formulas we derived earlier. So in going through this Julia function, it's a little bit longer than what we have covered before. The correctness depends on the correctness of the formulas that we derived for the coefficient matrix. You see what is on the diagonal, and you can kind of see from here already, since this is a two-dimensional loop, that this linear system will actually be a dense system. So we are assigning to every element in the matrix. Again, for big M and big N, so this is quite abstract, and in general, one should run the code and step for step look at the numbers. Then we solve this. So you can see how big matrices come in here. Here we do this simply with the backslash operator. But in practice, one would do something like multi-gridding, start with a very coarse grid, and then use the solutions on the coarse grid to go to a finer and finer grid, and thus then applying iterative methods to proceed. Assuming again nice continuous functions that are twice differentiable. So this simple function will do it all. Let's look at the numbers. So in the previous two lectures, the first experiment that we did, it always ended out in a catastrophe. But since this is now the last lecture, it actually works extremely well. So even for a 4×3, so if we are solving for a 12 variables, we actually find an approximation. So remember, the exact solution was x squared minus y squared. It works almost too good to be true. We have full machine precision. Wow. So this is quite the opposite of the catastrophic catastrophic calculations that we did in the first two lectures. So sometimes it works out very, very well. And why is that? Well, I leave this over to the second exercise. Why is the error actually so small? So the central difference formulas would actually predict an h² error. However, notice also that our function is actually a simple quadratic. And in a way, what we do with central differences is a little bit similar to interpolation. So think about applying central differences to compute derivatives. So this question here comes in the context of partial differential equations, but it comes back to the problem of numerical differentiation. So sometimes numerical differentiation works extremely well on extremely nice functions. Interpolation works with differentiation, provided that your what you are differentiating is also very close to a polynomial of degree 2 here. All right, here is a more interesting example where now it's again, you can verify that we know the exact solution. So if you take the derivative of the natural logarithm, you have the inverse. So then you can verify that taking once more the derivative will give you the condition that you need. Also here important that we should not take the natural logarithm at 0. So the domain is also constructed to make sure that this problem really makes sense. So this is another example. And with this example, now it is done on a 3×3 grid. So we are perhaps a little bit emboldened by our success on the first example. We now see that on the 3 by 3 grid, we do have an error. Although when it is printed here with 4 decimal places, we can see that we have 3 decimal places correct if we round. So if we round off to 3 decimal places, then the solutions would again agree. So important here to interpret the errors. So the numbers that we obtain comparing the exact solution with the approximation, can we explain what we observe? Well, let's try to do this. We have the formulas for the step sizes, h and k. We also know that the central differences are quadratic. So we have estimates. So the big O here means that there is somehow a constant still. It's not entirely in the asymptotic sense, but there are some constants, and the constants here were less than 1. So for this very nice, still very nice solution, we actually were observing an error that is less than the theoretical error. So the h square and the k square can be used to predict the order. So we were expecting about 2 decimal places correct, but we got 3. Here is another example. And this is the last exercise, which could be what you would get on a final exam. The last question. So the last question could often be given the solution, like on the previous slide. So sometimes one gets exhausted by the last question, but never gets to the last question. But the last question is not always the hardest question. All right, I am running out of time. I have still 2 minutes left for 2 concluding slides. So we have covered 3 lectures on partial differential equations, mainly as an application of what we have covered before. We spent very little time on numerical differentiation, but in the last 3 lectures it was all about finite differences, applying forward differences, which gave us an explicit method for the heat equation, which was not really accurate and could also completely blow up on us. Backward differences were unconditionally stable, but still not accurate enough. So for the heat equation, we actually needed 3 methods. We needed a third attempt that gave us the method of Crank-Nicholson, which was also the h square and the k square. With both the wave equation and the steady state equation of today, we were fortunate to get immediately an accurate solution. So here, because this is the last lecture, we actually did not have to worry about the stability. However, know that the system that we get is immediately m times n. So this is not a time-stepping method anymore. We immediately have to solve a very big linear system. So this course, what we need to really remember of this, so numerical analysis studies algorithms for continuous mathematics. So it is at the intersection of computer science and mathematics. If one does not understand the mathematical theorems, then one cannot get accurate results. So in a way, we derive algorithms which can be completely logically correct, but which can give on certain inputs completely meaningless results. So that makes numerical analysis both difficult, but both very, very interesting. So in this course, we follow traditional calculus-based approach. So it's fundamentally important that we realize that the floating point arithmetic is completely different from our computations with real numbers. So we then considered the problem of conditioning and numerical stability on root finding, linear system solving, interpolation, and data fitting. And the second part was completely oriented towards differential equations, where we applied numerical differentiation and integration. Two important issues. We first examine whether our problem is well defined. We do this with benchmark problems, but also with, in general, looking at the conditioning of the problem. If the problem is ill-conditioned, ill-posed, no matter how hard we work, it will not work. But we study for well-conditioned problems numerically stable algorithms. We can study, there is the trade-off between accuracy, how accurate we can get with as minimal amount of work. So this concludes this course.